Okay, yes. Okay, so we're ready for, that's the third lecture, right? The third lecture of the lecture series that we organize in a consortium of various universities. And today we'll have Professor Anna Frebel. She's an astronomer and an astrophysicist. She received her PhD from the Australian National University. She did postdoctoral work at the in Austin, Texas, and also at the Harvard-Smithsonian Center for Astrophysics. And she's now a professor at the Massachusetts Institute of Technology. And she's a stellar fossil hunter, I guess. She is well known for finding some of the most chemically primitive stars that tell us something about the beginnings of element synthesis. She even has a star that's informally referred to as the Frebel star. So her work has been really, really important for nuclear physics. Her data is what we compare our models to. She's also very active in mentoring activities for students, and I hope she's going to tell us a little bit about that too. I don't know. She's also well known for publicizing science. She actually wrote a book. I think the German book came out first, but there is also an English version, I think, right? Searching for the oldest stars. It's a virtual meeting, so we can't have book signings. But anyways, we're really excited to have Anna here, and she'll tell us all about old stars, I guess.
Yes. Well, thanks for this very nice introduction, Hendrik. You can ask me about mentoring and career development at the end if there's time. No problem. Today, I would like to tell you a little bit about a dwarf galaxy called Reticulum 2 and what happened to that poor little thing a long time ago, and what exciting things we have learned from studying this object. I want to start the story a little bit differently, though. Let's go back to the time after the Big Bang, some 13.8 billion years ago. The universe was just hydrogen and helium at the time. And from that primordial gas, the very first stars formed, because hydrogen and helium gas is very simple. You actually end up with very big stars because the gas can clump a lot. So you have stars that are about 100 solar masses, and that means that they explode really quickly. And so the very first elements heavier than hydrogen and helium were expelled into the universe, because that's what was made in these first stars. And from that slightly enriched gas, all the second and later generations of stars formed. And now smaller stars could form, ones with less than 1 solar mass, and they have very long lifetimes. They also don't explode. And those are still observable today. And these are the ones that we are chasing in our Milky Way and in small dwarf galaxies. And I have a quick video here that shows you how the Milky Way formed. And I want you to look at the red and the yellow spots, because those were the locations where the first stars and then also the first galaxies formed. And you will see how they actually get brought into the Milky Way, which is emerging within that white circle. So you see lots of spots all over, following along these streams of gas. And then the Milky Way assembles there as the bigger thing in the middle that's eating up the little neighbors. And there it looks like a big beehive. Everything's swirling and swarming around it. And we see many of these smaller clumps a little bit further out there as dwarf galaxies orbiting the Milky Way today. And we'll come back to this sort of idea of this hierarchical assembly, so bigger systems eat smaller systems to grow, towards the end of the talk. I want to first continue to talk a little bit about chemical evolution. If you imagine that purple cloud to be the primordial gas after the Big Bang, then the first stars, as we said, formed from that. They made heavier elements, heavier than hydrogen and helium, in their cores for energy generation purposes, and then expelled all of this material during their supernova explosions. And so this material gets put back into the reservoir. And then with every generation, and every generation does contain massive stars that turn into supernovae, this gas cloud gets enriched in all the elements more and more with time. And as a consequence of that, it means that the younger stars, like the sun, that formed perhaps after 1,000, this cycle going around 1,000 times, they contain a larger amount of heavier elements than the stars that formed when this cycle had only gone around a few times. And that is the key to searching and finding the older stars, namely that we look for stars that have the least amounts of heavy elements in them, because it does imply that this cycle here had only gone around once or twice or 3 times or so. And to put some numbers to that, the sun contains about 1.4% of heavy elements. Again, after the Big Bang, that was 0. It took 8 billion years for the universe to come up with conditions that that contained 1.4% of heavy elements. In comparison, our old stars, not quite 0. That would be the first stars at the time of their formation. But we have something like 10 to the minus 4, 10 to the minus 7%. So it's very, very little. And I'm a spectroscopist. That's how you find out about the chemical composition of an astronomical object. If you look at these 5 different spectra there, or 4, you see the sun at the top, and then lots and lots of absorption lines below the dashed line there. That's not noise, it's just many, many lines, very strong, all overlapping. And a few elements are labeled. And if you then go down one spectrum to another, you'll see that we basically dial down the element content. So we're going back in time. And you can see that the spectra are much cleaned up. And at the bottom one, there's only one tiny little line left. I hope you can spot it. That's an iron line there. And we think that that bottom star is of the 2nd generation. So that's one of the first low mass stars to have ever formed in the universe. Now, there's one more thing that we need to clarify here in terms of jargon, so we all understand each other. You see a periodic table there, but the universe is a complicated place. So someone clever a while ago said that, well, why don't we call hydrogen X and helium Y, and all the rest we call Z, and say metals. So of course, chemically speaking, neon is not a metal, but as an astronomer, I'll get away with that. And so all the other elements are called metals, except for hydrogen and helium. And consequently, and this is an important point, the stars that we're looking for, these old stars that form very early on in the process of chemical evolution, they are the most metal poor ones. So they have a lower heavy element content than the sun, which is our reference star. So again, we call them metal poor stars. Now, I already mentioned in passing that stars make heavy elements due to energy generation purposes. And I just wanted to quickly go over this. So we have fusion that goes on in the center of stars. And you can generate energy from fusing lighter atoms to heavier ones. And that goes all the way up to iron, as you've just seen in this cartoon. If you try to smash 2 iron atoms into each other, it will cost energy. And that's obviously fatal for the star, because the star needs the energy to shine. Consequently, once a massive star that goes through all these burning stages actually has an iron core in its center, it will explode as a supernova, because indeed the source of energy ceases, and that leads to a collapse and then a disruption of the star. So tough luck for that, but you've seen at least 2 periodic tables already. And you know that there are many, many elements that are heavier than iron. So where do they come from if they are not made in the centers of stars? And the answer here is that they're made in so-called neutron capture processes. The basic idea is fairly simple. You start with a seed nucleus like iron that you see on the left, and then you bombard that seed nucleus with neutrons. So that's illustrated here. And so that poor nucleus swells, becomes a neutron-rich isotope. And then once the neutron flux stops, it decays to a heavy element. So one of the heavier ones. And in the interest of time, I don't want to go into too much detail, but show you another graph here. Actually, can I just say, Anna, have we already missed one of the polls?
Could be, but here it goes.
Okay, so why don't we take a quick break here and do a poll? I've added those. It's the first time I'm running polls, so I can't see any. I can only hear. I can't see the poll either. I don't know if that's so. Ah, I can see the poll now. Great.
Sorry, that was relaunch.
Oh,
there it goes. Now,
okay,
click on your favorite. Okay, last chance.
Yeah. Perfect. I guess I'll just say it is B. It is not fewer elements. It's fewer of all the elements. So that's actually, I added that because that's a very important distinction that is often misunderstood. It's just less of all the amount. It's a smaller amount of all the elements, because as I will show now and try to convince you all, that really almost all the elements are kind of made from day one, just in small amounts, and then it adds over time. All right, so exactly how does this work? You've seen the cartoon. Here's an actual simulation from a colleague. What happens here is we have this charts of the nuclei. So neutron go on the x-axis in the horizontal, and then the vertical axis is protons. And the little black squares are stable isotopes, and whatever is underneath the stable isotopes are the neutron-rich isotopes that want to decay. And so those are created from that neutron bombardment. So it's going to start at the left top, the bottom left corner with the seed nuclei. In this case, the seed nuclei are hydrogen, but it makes no difference really. And then it's going to shoot up all the way to the transuranian region, so the gray area at the top right. And at some point, the neutron flux will stop, and you will notice that because suddenly that big colored cloud is going to move diagonally towards those little black squares. And that's a very important moment once this starts to diagonally move, because this is when an associated kilonova with an event like that becomes observable and gets powered. So let's look at this. All right, so here we go. we have this neutron bombardment that successively produces these neutron-rich isotopes within a matter of a second. We're at half a second now, and there it already stopped. The neutron flux already stopped after 1 or 2 seconds. And now it's decaying diagonally back with a beta decay to those stable isotopes in little squares, in the little black squares. And this is probably the only astrophysics simulation that actually takes longer to show than it takes in nature. The other video that I showed was billions of years crammed into 30 seconds. And you can see here, it takes about 2 or 3 weeks. Now we're at longer time scales, but not much is happening anymore. So 2 or 3 weeks for the majority to get to most of the stable stuff there. And if you are familiar with LIGO and kilonova, and that's the product of a neutron-star merger that was observed by the astronomers following the trigger by the gravitational wave folks that this event had happened. So this kilonova is powered by the radioactive decay of these neutron-rich isotopes that you just saw here. So it's really a fantastic way to observe nucleosynthesis in action. Because, yes, it's happening inside of stars, but you can't really see inside of the star. You can only see the light coming out of the star. Anyway, we'll talk a little bit more about neutron-star mergers in a moment. I just wanted to show you how this works here, because if you now take all these stable isotopes and you add them up into elements, then we can look here at the periodic table and see, like, okay, which elements are actually created by this process, this rapid neutron capture process. And you see all the blue elements are created this way, right? Everything below at the bottom half there. There are some transition elements that you see there in gray, in brown, sorry. We don't need to worry too much about that. So all of the ones there at the bottom. And just for comparison, there's another neutron capture process. It's a slow one. It operates differently. It also gets you all the elements, but actually in different isotopic compositions, right? Because every element is made from different isotopes made in the process that you just saw. And the big difference here is that thorium and uranium there at the bottom are not made in the S process. They can only be made in the R process. So that's what makes that R process really special. And then, of course, it's also important to look at what is actually happening in terms of chemical evolution. So the 2 periodic tables that you just saw were basically the product of just one event, right? One R process event, one S process event, and then what comes out of that. If we now apply this sort of to a real life example and look at the sun formed from a bucket of gas that is a product of 8 billion years of chemical evolution. So 8 billion years of supernova explosions, R processes, S processes, everything process, just all goes in there. So the isotopes created in all these processes get mixed around a fair bit, and then you can see now that all the heavy elements, they are actually made in different proportions by the S and the R process elements. So you can't judge a book by its cover. If you look at the barium book, it would be mostly the S process that made whatever barium you see in the sun. But if you look at europium, that's at the bottom there, 63, most of it comes from the R process. So if you just measure the element, it's not going to tell you that. Luckily for the sun, we have enough information that we can get to the isotopic compositions, but it's actually quite difficult, not possible for other stars. So what that means is if you want to measure the clean signature of one of these processes, you have to find yourself a star that formed, that has none of this junk in it, but only formed right after one of these events actually occurred, so that your star then incorporates and preserves that and only that nucleosynthetic signature. And that's what we're trying to do with old stars. because we're preempting a whole lot of chemical evolution. We're just going back to the very beginning when the universe was still pretty clean and neat.
Is it time for another question?
Yeah. Yes, great. Yeah. Okay, and now people are starting to vote. Okay, a few more people.
Okay, anybody else?
That is actually C, radioactive beta decay from the neutron-rich isotopes, right? This charts of the nuclei. The nuclear fusion does power the star, but it does not power this kilonova event. And I apologize, I didn't give too much information about that. All right, let me see if I can. Oh, no, I can't see my mouse here, and I have this big pole in front of my screen now that I can't. Like, I think maybe this.
It didn't.
No, okay, now I got it. Yeah, I have to fish a little bit. All right. This process that makes the heavy elements, is something that people have been thinking about for a long time, since 1957. And already back then, they really wanted to figure out, how are all the elements made in stars? And they're saying here about the process, amongst others. Observational evidence can be obtained only by interpreting the spectra of type 1 supernova, a problem which has so far remained unsolved. Well, they were halfway right and halfway wrong back then. Interpreting the spectra, yes, totally. Type 1 supernova, not so much. Problem which has so far remained unsolved, well, we're finally getting there, but it's almost 60 or more than 60 years later by now. So we're using old stars and the spectra of those to indeed catch the signature of this process. And here is an example. So when you take the abundances of all these blue elements and you plot them up against their atomic number, then you get this blue pattern there. For comparison, the purple pattern is that of the S process, and you can see there's a big difference between the two. So if we then find a star where we can measure all these heavy elements in it, we can pretty clearly say, like, okay, do these elements come from the S process or from the R process? And here we can clearly see that it's from the R process, because the red dots match up with the blue pattern. They match up actually so well, and they do that for all stars, that we're saying that this is a universal pattern. Somehow whatever makes these elements in those stars, that we find in those stars, that were not made in the stars themselves, somehow it always works in the exact same way, because we can overlay these patterns and they match, right? The blue line is not a connection of the dots, it's just overlaid and it perfectly matches. So this red dot star here is what we call an R process star. So it formed after an R process event had occurred. All of these R process elements got spilled into the gas cloud, and from that our little star formed, which you then observe 13 billion years later or so. Where exactly are we searching for these stars? We do that in the Milky Way, mostly in the outer parts, as well as small dwarf galaxies. These R process stars are very rare, only 3 to 5% of old stars that are already rare. So we're really looking for a needle in the haystack. And this number isn't quite up to date, but I think we have about 70 stars of those now. So very, very rare still. The problem with finding these stars in the Milky Way is that we don't actually know what the origin of these stars are. if you remember this early video about the hierarchical assembly of the Milky Way, right, how it formed and how it ate all its neighbors, you can see that much of what is in the Milky Way right now actually did not form in the Milky Way. It was brought in through these continued accretion events. So the origin of probably all of the oldest stars now located in the Milky Way is actually outside of the Milky Way. They were born in one of the first galaxies in some small systems close by, and the Milky Way eventually ate up those little systems and inhabited those and incorporated those stars into the Milky Way. And as you will see in a little bit, this is actually a problem if we don't really know where these stars are coming from. So to recap, everything that I mentioned to you falls under the umbrella of stellar archaeology, which means that we have a big telescope in Chile and we search for little low mass stars that have long lifetimes in our Milky Way. And we hope that we search for the most metal-poor stars, and then we determine their chemical abundances from the spectra. And we get this abundance pattern. And that actually basically equals the chemical composition of the birth gas cloud, that green one, the teal one on the left, and that's the gas from which these stars formed. And the question is, how did these elements get into that star-forming cloud? And that's a big part of our job. Was it a big star? Was it a small star? What kind of event was it, right? How did in case of the R process, how did these R process elements get into this early gas cloud so that these little stars that we're finding today could form from that? And then the little guys actually just hanging around and preserving that composition of this early gas cloud for us for billions of years, because these little stars are actually really boring. They're just burning hydrogen to helium in their cores and the outer atmosphere. They don't care at all about what's happening in the center. So it's perfect preservation. And just to put a quick number to it, for those of you who are interested, the stars that kind of in the one that are in a regime where there's only one progenitor object or one progenitor nucleosynthesis event. That's a sort of iron over hydrogen in the bracket notation of less than -3, which really means it's less than 1,000 thousandths of the solar iron abundance. Again, talking about metal poor stars, or quite metal poor. This is a range where these stars could all be second or third generation stars, so very, very old and ancient ones. Overall, this kind of work makes metal poor stars a local equivalent to the high redshift universe, where far away galaxies are used whose light has traveled to us for billions of years. We don't need to wait that long. These stars are in our galaxy, just a few thousand light years away. But they simply are very old, and so they have already preserved that information. All right, so for the second half of the talk, we'll have to talk about dwarf galaxies. So this is a picture of lots of little dwarf galaxies swirling around the Milky Way. And we're going to talk about Reticulum 2 there at the bottom in this red square. And here's Reticulum 2. If you look on the left, you'll see lots of stars, but that's just all stars in the direction of Reticulum. If you remove all the foreground stars, you're gonna see not much. If you have a few smudges on your screen, you'll probably see more. So that's an ultra faint dwarf galaxy that only has a few thousand stars, and is difficult to spot, and members are really hard to discern and to even work out that there's a proper galaxy. I think we'll have another poll now. And while we're waiting for that, you can see the beautiful Milky Way, the center of the Milky Way rise over the telescopes there. That's a little time series thing that I made a few years ago while observing dwarf galaxy stars with the left telescope. It's very pretty, I think. So that's in Chile there.
It is. How long did it take to take that
That's
movie?
one night, kind of.
Pretty cool.
Yeah, so quite like 6-8 hours. Every few hours I had to run and exchange the battery, making sure not to move the camera to, you know, change the view. Great. So the answer is 60 plus years. So really quite a long time that people have tried to work out the mystery of surrounding the R process, because I should just say that, because we're getting to that in a moment, I haven't really told you where that R process happens, only that it happens. And that's what we have been stuck with for that long. But a few years ago, there were new clues, and I'll reveal them in a moment. So anyway, so this is just a pretty little movie here. And for those of you in the know, there's a color magnitude diagram right next to it showing the brightness of these stars in dwarf galaxies, 17th, 18th, 19th magnitude, very difficult to observe even with large telescopes and high resolution spectroscopy. But we did it, and here are the spectra. They look really terrible, but that's what you get for faint stars. What's important is that you have a lot of lines there where the blue dashed line is, and those are barium and europium lines. I should say here that nobody had seen such strong neutron capture elements in any stars, in any dwarf galaxy before. So when we had these data, we were very, very surprised. And I was like, what's going on in this little dwarf galaxy? But we're seeing europium lines, and europium is a smoking gun of the R process. So my former grad student, Alex G, he measured the abundances, and you can see now in purple is the R process pattern, and the black dots are the data points, and you can see that they match the purple line, not the golden S process. So what I joked about up first became a reality, namely that this is an R process galaxy. So some R process has gone off in this dwarf galaxy, and then all these stars form from that enriched gas. And now we have environmental information because we know that these stars are in a dwarf galaxy right now. And they probably formed there too, because it's a really small system. And so that is what makes a big difference. Here are the abundances, just to highlight, you know, what kind of whopping abundances we found there. The bright red ones are the reticulum abundances. The other colored points are other dwarf galaxy stars, and you can see that they're very different and much lower, especially in barium. Europium upper limits are often a bit meaningless when they're too high. And in gray, you find sort of the Milky Way stars, whose origin we don't exactly know. But you can clearly see that we have very high abundances and compared to what's typically found everywhere else. And the other high gray points are these 70 R process stars that we found before. All right, so to cut a long story short, because we're a bit short on time, what we think is that a neutron-star merger, went off in reticulum 2, and with LIGO it was shown also that when you have two neutron stars merge, then an R process can occur. That had been theoretically predicted, but we had been lacking the observational confirmation of that. Now, one quick word on neutron stars. They're not actually stars. A star needs to have fusion for energy generation purposes. A neutron star is just a small ball of neutrons, but if you want to make the R process, you need neutrons. But you can have them in a binary system, so two orbiting each other. And over time, sometimes it takes a while, they will lose a little bit of energy and they will eventually in spiral and then merge, and then push, this merger event happens. And as part of that, there can be this afterglow, which is what we call this kilonova that I showed to you earlier. And to put some details here, a lot of these neutron capture elements can be made in a neutron-star merger, but the problem is it takes just a little bit too long. Many of us stellar archaeologists, we didn't like that it could take a long time, but we made our peace with it. There are some ways. You can ask me separately about that. And then what's important is that, you know, how much comes out, and we have this 10 to the minus 4.5 solar masses of europium that we get per event. So that's actually quite a lot. And so this is sort of in the merger phase, and there's sort of S processing happening in multiple locations within this merger. It's very complicated, this merger procedure, and many theorists are working on this. There's a lot to learn still. When you take this yield of 10 to the minus 4.5 solar masses and you calculate, it's actually a very simple calculation, how much, you know, if you dump this into 10 to the 6, so 1 million solar mass of hydrogen gas, what abundance should your star have that forms from this enriched gas? And as it turns out, if you do this, you get this orange bar that overlaps with the red data points, right? We get the big bar because we have limits only on the mass of this galaxy. We can't pinpoint it great. So it gives us this bracket. But you see, it's a fairly good match. And just for comparison, in brown, I'm showing other bars there that come from, if you were to assume the R process occurs in a supernova, which actually the supernova doesn't have enough oomph to make all these elements, so it produces at best very little, and so it ends up being down there. And so supernova probably did not contribute these R process elements in the case of reticulum-2. So that brings me to my summary.
We have a couple of questions.
Yes.
Could we display the 2 questions?
Right, we have another poll. Sorry.
We have 2, so pick
Okay, then
favorite.
let's do that.
Okay, a couple more seconds, and I'm gonna end it.
Yeah, we have all answers there. It is ultra faint. I didn't say much about it, but a few thousand stars for a galaxy is very, very little. A globular cluster already has 1 million stars. So these are the wimpiest little galaxies out there.
And here's the last question.
Yes. I hope everyone gets that. Yeah, close.
Yep, good.
Great. So neutron-star merger. So supernova probably did not contribute heavy elements to reticulum-2. And the white dwarf binary I completely made up. Just for the fun of it. Yeah, wonderful. Again, I can't close this window here, but I guess I kind of know what's on the slide. So I hope I could give you a very short introduction to stellar archaeology and little dwarf galaxies and old stars, and showcase a little bit how we really go from the nuclei to the cosmos, from the really small things to the big questions. And yeah, there are more dwarf galaxies that we are trying to study now to find a second R-process galaxy. We found Reticulum 2 in 2016, but we haven't really found a good second one. They're sort of a candidate, but it's a bit controversial. And eventually we'll have a new telescope, a bigger, much bigger telescope, the giant Magellan telescope. And this work will be a little bit easier with that one, but we'll probably have to wait another 10 years before that one's operational. If you like this kind of topic, as Hendrik kindly already mentioned, I've written this book. Christmas is coming up, so maybe you want to get it for yourself, or you know, gift it to someone else. If you're not much into reading, but rather than watching stuff, also have a YouTube series, 11 parts, Cosmic Origins of the Chemical Elements. That's sort of the short version of the book, and a little bit broader than what I could tell you today in the limited time that we had together. So with that, I think that's all for me, and I'm happy to take questions.
Thank you, Anna.